Swayam Prabha. Digital India. Educated India.
Now, shall we start with eigenvector computation and low rank approximation, next idea. So, in the previous section, we related to principal component analysis and orthogonally how it done the points, and here we are going to discuss the eigen decomposition and largest eigenvalues related to principal component analysis. So, now we obtained the basis of principal subspace as the eigenvectors and that are associated with the largest eigenvalues of the data covariance matrix. So, S equal to 1 by n summation n equal to 1 to n xn transpose equal to 1 by n into xx transpose. So, x equal to x1, x2 and so on, xn belongs to R power d cross n. Note that X is a d cross n matrix. Now, it is a transpose of a typical data matrix. To get the eigenvalues of S, we can follow the two approaches. Number one, we perform an eigen decomposition and compute the eigenvalues and eigenvectors of S directly. We use the singular value decomposition since S is symmetric and factorize into xx transpose, and ignoring the factor 1 by n. The eigenvalues of S are squared singular values of x. And more specifically, the singular value decomposition of x is given by x equal to d cross n matrix of x. So, we have a U and U is an orthogonal matrix, and V is nothing but the transpose of U of P orthogonal, that is also orthogonal, and U is a d cross d matrices, and we have a summation is running, but the matrix belongs to main diagonal of this, and then summation is also R per d cross n and V transpose n cross n. Therefore, the resultant is d cross n, and we have a d cross n, and a d cross n to d cross n is we have a d cross n. So, d cross n matrix will come, and U belongs to R power d cross t, and V transpose belongs to R power n cross n, or orthogonal matrices, and summation belongs to R power d cross n is a matrix whose only non-zero entries are singular values sigma ii is positive. So, it follows that S equal to 1 by n to xx transpose, and this can be written as 1 by n into U summation V transpose and V summation transpose U transpose, and this belongs to I, and summation transpose is I, therefore U transpose, then it satisfies S. So, the result of this section, we get the column U or the eigenvectors of xx transpose. Furthermore, the eigenvalues of lambda d of S are related to the singular values of x through lambda d equal to sigma d square by n. So, this relationship between the eigenvalues of S and the singular values of x provides the connection between the maximum variance and the singular value decomposition exists. So, we are going to discuss principal component analysis using low rank matrix approximation to maximize the variance of projected data or minimize the average squared reconstruction error, and PCA chooses the column of U in the equation 48 to be eigenvectors that are associated with the m largest eigenvalues of the data covariance S, so that we identify U as the projection matrix B, so which projects the original data onto the lower dimensional subspace of the dimension M. So, the Eckart-Young theorem says that offers a direct way to estimate the low dimensional representation, and the best rank M approximation is xm equal to argument of minimum of rank A is less than or equal to M, which is norm of x minus A belongs to R power d cross n, where norm dot is a spectral norm and already defined, refer it. So, the Eckart-Young theorem states that xm is given by truncating the singular value decomposition at the top M singular value. In other words, we obtain xm bar equal to um, where um is a data identify U as a projection matrix of B, and summation is a matrix belonging to the diagonals of the given matrix A, and Vm is nothing but the corresponding vectors of orthonormal transpose of U, that is Vm transpose, and then Um is D cross M, and summation M is M cross M matrix, and Vm is M vectors of R power n cross M values. So, Vm transpose is M cross n, and these are the orthogonal matrices from the given matrix A, and simply using this format, so that xm will get it. So, xm is singular values of these values of A. Therefore, this is the largest singular values of x, and the diagonal summation is R power M cross M of the diagonal entries, and capital M is the largest singular value of x. Now, we are going to discuss the practical aspects. Finding eigenvalues, eigenvector is also important in other fundamental machine learning method that require matrix decomposition. In the theory we discussed, we can solve for the eigenvalue as a root of the characteristic polynomial. However, for the matrix larger than 4 cross 4, this is not possible, because we would need to find the roots of the polynomial of degree 5 or higher. However, the Abel-Ruffy theorem states that there exists no algebraic solution to this problem for polynomials of degree 5 or more. Therefore, in practice we solve the eigenvalues or singular values using the iterative methods, which are implemented in all modern packages for linear algebra. So, in many applications such as principal component analysis presented in this chapter, we only require a few eigenvectors, and it would be wasteful to compute the full decomposition and then discard all the eigenvectors with the eigenvalues that are beyond the first few. And it turns out that if we are interested in only the first few eigenvectors with the largest eigenvalues, then the iterative process, which is directly optimize these eigenvectors, are computationally more efficient than the full eigen decomposition. In the extreme case of only needing the first eigenvector, a simple method is called as power iteration. It is very efficient. Power iteration chooses a random vector x naught that is not in the null space of S, and follows the iteration x suffix n k plus 1 equal to S into xk by norm of S xk, where k equal to 0 to infinity. So, this means that vector xk is multiplied by S in every iteration and then normalized. That is, we always have norm of xk equal to 1. So, the sequence of vector converges to the eigenvector associated with largest eigenvalue of S. So, the original is Google PageRank algorithm uses such an algorithm for ranking the web pages based on their hyperlinks. Next, principal component analysis in high dimensions. In order to do the principal component analysis, we need to compute the data covariance matrix in d dimension. The data covariance matrix is a d cross d matrix, and computing the eigenvalues and eigenvector of this matrix is computationally expensive as it scales cubically in d. Therefore, PCA, as we discussed earlier, will be infeasible in very high dimensions. For example, if our xn are images with 10,000 pixels, example 100 into 100 pixel images, we would need to compute the eigen decomposition of 10,000 cross 10,000 covariance matrix. In the following, we provide a solution of this problem for the case that we have substantially fewer data points than the dimensions, that is n is very small of d, and assume we have a centered data set x1, x2 and so on xn, where xn in r power d. Then the data covariance matrix is given by Sn equal to 1 by n into xx transpose belongs to r power d cross t, where x equal to x1, x2, xn in d cross n matrix whose columns are the data points. So, we now assume n is very smallest than d, that is number of data points is smaller than the dimensionally of the data. If there are no duplicate data points, then the rank of the covariance matrix S in n. So, it has a d minus n plus 1 many eigenvalues that are 0, and intuitively this means that there are some redundancies. In the following, we will exploit this and turn the d cross d covariance matrix into n cross n covariance matrix whose eigenvalues are all positive. So, in principal component analysis, we end up with the eigenvector equation S into Bn equal to lambda m into Bm. So, take the covariance matrix and corresponding B basis vector of the principal subspaces, do that, and find the eigenvalues corresponding to this to be determined, and SBm equal to lambda m into Bm, where m equal to 1 to m. Here Bm is a basis vector of the principal subspaces, and we got the eigenvalue. Once you get the eigenvalue, find the eigenvector. So, based on the covariance matrix S, we obtain 1 by n into xx transpose Bm. So, xx transpose is I, therefore, 1 by n into Bm corresponding to this one is a lambda m into Bm. Now, we multiply x transpose on both sides of the left hand side. What happened? This will yield what 1 by n into x transpose x into x transpose Bm. So, x transpose x is n cross n and x transpose Bm is Cm. Now, we have x transpose x corresponding, this one is lambda m, and lambda m into x transpose into Bm will come. So, we can write this expression will be equivalent to 1 by n x transpose x into Cm equal to lambda m Cm. We get a new eigenvector and eigenvalue equation, and lambda m remains eigenvalues, which confirms our result from this section that the non-zero eigenvalues of xx transpose equal to non-zero eigenvalues of x transpose x. So, we obtain the eigenvector of the matrix 1 by n into x transpose x belongs to r power n cross n associated with lambda m as Cm equal to x transpose Bm. Assuming we have no duplicate data points, this matrix has a rank n and is invertible. So, this also implies that 1 by n x transpose x has the same eigenvalues as the data covariance matrix S. But this is now an n cross n matrix, so that we can compute the eigenvalues and eigenvectors, and is much more efficiently than for the original d cross t data of covariance matrix. Now, we have the eigenvectors of 1 by n x transpose x. So, we are going to recover the original eigenvectors which we still need for principal component analysis. Currently, we know the eigenvectors 1 by n into x transpose x. So, if we left to multiply our eigenvalues eigenvector equation with x, we get 1 by n x x transpose x Cm. So, this is called as S, which is lambda m x Cm. So, we recover the data covariance matrix again. Now, also means that we recover xCm as the eigenvector of S. So, note, we want to apply PC algorithm that we discussed in this section. We need the normalize of the eigenvector xCm of S, so that they have a norm 1.